Hello, welcome to our short video on how to design a high-side current sensing circuit. This schematic represents a high-side current sensing circuit. Current sensing circuits are used to convert and amplify an input current, also known as a load current, to an output voltage. In this high-side current sensing example, a discrete difference amplifier is used to convert the load current to a voltage. Note that there are other ways to perform high-side current sensing, such as using an integrated current sense amplifier. In this circuit, the shunt resistor, R1, is placed on the high side of the load to create a differential voltage dependent on load current, which is then amplified to create a single-ended output voltage. High-side current sensing allows for the system to identify ground shorts and does not create a ground disturbance on the load. The transfer function of this circuit is composed of two parts, the current to voltage conversion and the voltage amplification. The first term, I sub n times R1, is the current to voltage conversion. In a difference amplifier circuit, if R2 equals R4 and R3 equals R5, the voltage amplification simplifies to R5 divided by R4 to give us our second term. The design goal for this circuit is to convert an input current range from 50 milliamps to 1 amp to an output voltage range from 250 millivolts to 5 volts. An output voltage swing of 250 millivolts to 5 volts will maximize the linear output voltage swing of the operational amplifier for a typical ADC input voltage range. The first design step is to calculate the shunt resistance R1 based on the maximum load current of 1 amp and maximum voltage across the shunt. For this design, we will set the maximum voltage across the shunt to 100 millivolts. To calculate the shunt resistance, we simply divide the maximum voltage across the shunt by the maximum load current, which yields a value for R1 of 100 milliohms. The next step is to calculate the gain of the circuit, which is calculated by dividing the output voltage swing by the input voltage swing. Remember that the input voltage of this circuit is equal to the load current times R1. So the gain is calculated by the output voltage swing divided by the load current range times R1. The gain of the circuit is calculated as R5 divided by R4 because R2 equals R4 and R3 equals R5. Choosing a standard resistor value of 1.01 kiloohms for R4 allows us to calculate a resistor value of 50.5 kiloohms for R5, which gives us a gain of 50 volts per volt. Next, we need to calculate the common mode voltage, or VCM, of the amplifier. This is to ensure we are operating in the linear region of the amplifier. The common mode voltage is calculated as VCC times R3 divided by R2 plus R3 and is equal to 35.294 volts. Since the OPA 192 is a precision rail-to-rail input device and the supply voltage is 36 volts, we are operating within the linear range of the amplifier. A DC sweep of the input current from 50 milliamps to 1 amp yields an output voltage from 255.65 millivolts to 5.003 volts. This verifies the functionality of the circuit. Running an AC sweep analysis, we find that the bandwidth of the circuit is 205 kilohertz. When designing high-side current sensing amplifier circuits, there are a few design notes to be aware of. First, ensure the common mode voltage is within the linear input operation region of the amplifier. In this case, we use the Precision OPA 192, which has rail-to-rail inputs. Next, increasing the shunt resistor increases the power dissipation of the circuit. Finally, the DC common mode rejection ratio performance is dependent on the matching of the gain setting resistors R2 through R5. Texas Instruments has many online resources to help you design circuits with op-amps. This includes reference designs and guides, educational videos, simulation and prototyping tools, support resources, and search tools. Thank you for taking the time to watch this short presentation on how to design a high-side current sensing circuit. Please visit www.ti.com for additional information and resources.